In the last hybridization video, we gave an overview essentially of hybridization, what it is. And so we talked about an older model essentially and how we can actually correct it to account for four equal bonds around carbon. And so we talked about the different possibilities of hybridization. We can essentially have four equal sp3 orbitals that are hybridized. We can have 3 sp2 hybridized orbital, or we can have essentially 2 sp hybridized orbitals. And so when we have 2 sp hybridized orbitals, that leaves 2 p unhybridized orbitals. When we have 3 hybridized sp2 orbitals, that leaves an unhybridized p orbital. And lastly, when we have 4 sp3 orbitals, we have 0 unhybridized p orbitals. So that's important to note, but this is kind of a higher level overview. This is not the way things are going to be tested on your exams. And so we need to look at a different vantage point essentially when understanding hybridization. So before we jump into that, I do want to discuss the size of the different orbitals and compare and contrast them. And so say size matters, despite what your professors might tell you. The orbitals all have different size. And so you have the s orbital. Actually, I won't include there. I'm just going to compare. Here is my sp3 orbital. It is the largest. And there is my sp2 orbital. And there is my sp orbital. And then the p orbital would stay like that with a node. All of these have a node there. So this is just an unhybridized and then these three are hybridized. So when we look at a molecule, is there a way to tell the hybridization of an atom? And so I say of an atom because each atom is going to have its own hybridization. So if I give you a molecule, for instance, say this is example, since it's this new video, we'll say just example 1. And so let's give you this molecule. We have to look at the hybridization of each atom. So typically they'll ask you what's the hybridization here, and so they'll identify which atom they're referring to. If we're talking about hydrogen, really we don't ever ask about this. It's not a high yield question because hydrogen always will have basically a 1s orbital, right? And so no matter where hydrogen is, it's going to be 1s. So we don't really ask about that. We do ask, however, about carbons. And so we look for how many electron domains carbon has. And so let me go ahead and create a table. So groups or electron domains and then we look at the geometry. And then lastly, we look at the bond angles and the hybridization. All right, and so when we look at this example, we're going to see there are 2 domains around this carbon. So let me actually change the color. And so here is 1 domain in the blue and 1 domain in the green, right? So those are electron domains. If, to give you a contrast, I have a carbon with 4 hydrogens around it, that's going to have 4 electron domains. And if I give you another example of maybe oxygen that has a double bond, these lone pairs are going to count as a domain. That's a domain. That will be a domain. And the double bond in its entirety is one domain. It's not bonds, but domains, right? So the electrons around the atom and how they're essentially arranged. So here we have 2 domains. Here we have, I'll go ahead and point at all of them, 4 domains, 4 electron domains. And then here we have 3 electron domains. Now, those are just examples. Let's go ahead and build out our chart. So I'm actually going to erase, or I can move these aside, and I'll move these down. And so we'll continue with our table. And so essentially, in order to tell what hybridization each atom has, we figured that out via the domains. So if I were to ask, how can we tell the hybridization of an atom? We do that through electron domains. We can even do that through bonds. I'll explain what that means in a second. So when we look at this example, we see 2 electron domains, 2 groups around the carbon in question. So let me actually identify the carbon in question by putting it in red. So this is the carbon that we're talking about. It has 2 electron domains. And so we continue, anything with 2 electron domains, and we can almost see this in the shape, or we can see this in the shape, there's essentially 180 degree geometry here. So it's going to have 180 degrees. It's going to be called linear. Right? See how everything is essentially in a line? It's linear. So let me clean this up a bit. Again, we're looking at one carbon at a time. We're not looking at, it's not referring to every atom. So this is the carbon we're looking at in red. This is one domain around it, and then the other domain is in green. So total of 2 domains. I'll actually put that second domain in blue. So 2 domains around that carbon atom. And so they're arranged in 180 degrees from each other. Why 180 degrees? Why do we want it to be 180 degrees? Well, we want to minimize the repulsion between things. And so electron density repulses electron density. And so we want these atoms to be as far away from each other as possible. That's why when you see carbon, we don't draw CH4 like this. Why? Because we're bringing the electron density unnecessarily close, creating an unfavorable interaction. Instead, we create as far of a distance as possible from each other, and we end up getting something that has 109.5 degrees of separation between each of these atoms. And so I'll actually save this and move it. We can reuse it here later. But let's continue down. So the bond angle essentially is linear. I wrote that already over there. So the bond angle is linear, and then, excuse me, I have these reversed. So the geometry is linear, and the bond angle is 180 degrees. Bond angle is 180 degrees. And so the hybridization, when an atom has two groups around it, it's going to have sp hybridization, right? So whenever we have two electron domains around something, it's going to have sp hybridization. Now let's do another example. Let's do something with three groups around it. And so let's talk about this oxygen. Or another example could be this carbon. Oops. Let me get the geometry correct. We want to spread these out as far away from each other as possible. So how I draw it makes a difference. So when I go here, essentially I want to go 120 because that would optimize the maximum, or that would optimize for a maximum distance between anything with electron density, which are the bonds, right? And so in this case, the atom that has three groups around it is going to be the carbon. So that's the atom we're looking at, this guy right here. In this case, we're looking at oxygen. We could also be looking at that carbon. Both of them would have three groups around it. And so we'll go ahead and identify those. So this would be one group. That's one domain. That's another domain. And that's the third domain, right? So we'll just look at the oxygen for now because there's just not enough space to really make that clear. But then the carbon on the right hand has, let me get blue to indicate domains. So we have one domain there, one domain around there, and then one domain there. So both of these, this carbon in the red and the oxygen in the red, both of them have three domains around them. So three domains. Let me choose a different color. And actually, I'll go ahead and color these also differently so we can stay consistent. So three domains is going to mean we have sp2. So the carbon in question here is sp2 hybridized. The oxygen in question here is sp2 hybridized, excuse me. And then if I go back to that carbon over here with the two domains, it's going to be sp3 hybridized. Excuse me, sp hybridized. And so now let's fill out the rest of these. We said that it's 120 degrees and maximizes the distance between three domains or three groups. And so that would essentially be trigonal planar. So we write trigonal planar as our geometry. Again, we have three electron domains. I'm going to write that up a little bit higher so we can see that. Okay, and so now let's move to the third example. Let me move some of these things out of the way. Just bring this down a little bit further. And then we'll focus on the third possible. And that is a carbon. An example has four bonds around it. Anything with four domains around it. Not four bonds, because here we still have four bonds around this carbon there, and it's sp2 hybridized, right? And so it's not about the number of bonds around it, it's about the number of domains. You can have four bonds and have three domains. Let me clarify that a little bit more. So if I have this carbon has four bonds to it, but only three, let me zoom in here a little bit, three domains. You see that? Here are the domains in blue. 1, 2, 3, but it has a total of 4 bonds. 1, 2, 3, 4. Right? So starting to look unrecognizable, so let's get rid of that. So 4 bonds and only 3 domains. Now, here we have 4 bonds. 1, 2, 3, 4. And how many domains? We also have 4 domains. 1, 2, 3, 4. So this has 4 bonds and 4 domains. So remember, we can have 4 bonds to atoms, but different numbers of domains. So here we have 3, here we have 4. And so let's go back to building our table. Now, what we have essentially is 4 electron domains around this carbon. So I'll put the carbon in blue, and I'll go ahead and actually slide this over so we can have space to keep building our table. And I'll put in blue. And then now we have a geometry that's called tetrahedral. We're maximizing the distance between everything. And to do that, we're going to have a tetrahedral geometry. And so we talked about this in this example over here. 4 bonds to carbon in order to push them as far as possible away from each other, because we don't want that electron density. We would have 109.5 degrees of separation. And so around each of these, all of them would be 105. And so that gives us this tetrahedral shape down here. So it's tetrahedral. All right, and now let's continue with our table. So we said this is 120 degrees. This is 109.5 degrees. And this is going to be sp3 hybridized. All right, so there are the examples. We can have something that's sp3, we can have sp2, or we can have sp. So now let's just do a few examples where we try to figure out what exactly is sp hybridized, what is sp3, and what is sp2. So we'll do this example here. So let's see here. Start with this. I'll draw the lone pairs so that way it's easier for us to see. Let's focus on a few atoms. So let's go ahead and look back at this chart. Whenever we see 4 domains, we're going to have sp3. So if I draw the implied hydrogens around this carbon right here in blue, how many domains does this carbon have? 1, 2, 3, 4 domains, and therefore it's going to be sp3 hybridized. So this carbon right here, sp3 hybridized. Let's take a look at the domains around this carbon. So let's color it. What did we use to color sp3? sp2 was green. So we look at this carbon right here. Let's keep it green. And we look at how many domains. That's 1 domain, 2 domains, 3 domains. And so what do we end up having? We have sp2 hybridization. So let's draw that there. So that carbon sp2. Now let's look at oxygen. How many domains does it have? It has lone pairs. So this is one domain, that's another domain, that's a third domain. So 3 domains is going to be sp2. Let's take a look at this carbon. We have 1 domain, 2 domain, 3 domains. So it's going to also be sp2. Let's take a look at this carbon. 1 domain, 2 domain, and then there's a hydrogen. Let's see if I can. So that carbon, there's a hydrogen. Not drawing the angle correctly, but I just want you to see that it's a domain. 2 domains, 3 domains. So that's going to be sp2 hybridized. And then let's do this carbon on the end. We know there's an implied hydrogen there. How many domains are there? 1, 2. Therefore, it's just going to be sp. So I think we had sp in the red. There. And so to stay consistent, anything that's sp2, I'll just shade in green. This was sp2, that's sp2. Now, that's one way of figuring things out. The other way is essentially, let me give you another example. Very similar. We'll do when we look, any atom that has a double bond on it, this has a double bond right here, this has a double bond, that has a double bond, that has a double bond, that has a double bond. All of these have double bonds attached to it. So if we slow down a bit, not get too excited like I just did, right? This has a double bond, right? Here's the double bond that it's connected to. So does this. Anything with a double bond is going to have sp2. This carbon right here has a double bond to the oxygen, so that's going to have sp2. This oxygen has a double bond to the carbon, so that's sp2. This over here does not have a double bond, it has a triple bond. And so it's going to have sp hybridization. That has a triple bond, so it's also going to have sp hybridization. Do we see any other triple bonds? Okay, no. Anything with a single bond is going to have sp3 hybridization. So these only have single bonds. If we draw in the implied hydrogen, all atoms around that carbon, all bonds are all single bonds. There are no double bonds. And so therefore it's going to be sp3 hybridized. Same thing here. If we draw the implied hydrogens, there are 4 bonds around this carbon, and all of them are single, so therefore it's going to be sp3. Same over here, sp3. What about this right here? That's got a double bond to it, so anything with a double bond is going to be sp2. This also has a double bond attached to it, so that's sp2. This has a double bond to it, so that's sp2. So whenever we have anything, any atom with a double bond to it, it's going to be sp2 hybridized. Whenever we have any atom that has triple bond on it, it's going to be sp hybridized. And then lastly, whenever we have an atom that has essentially a single bond around it, just a single bond, it's going to be sp3. So this is single bond. I should say bonds. This should be triple bond. This is going to be a double bond. Now I can also have a triple bond in a different way. Let's say I have an atom that looks like this. Is this going to be sp2 or sp3? How many domains does this have? 2, right? So if we go up to our chart, we have 2 domains, therefore it's sp2. So this is, excuse me, sp. I misspoke. So sp hybridized, right? So a triple bond is a dead giveaway that it's sp. But don't just assume that a double bond is. You have to sometimes count the domains. So this, even though it has a double bond on it, it also has a double bond there, and therefore it has 2 domains only, so it's going to be sp. So obviously domain trumps, but the cheat sheet or the shortcut is essentially if it has a double bond. If it only has 1 double bond on it, if it has 2 on either side, again, it's going to be sp. And if it has all single bonds, I can even clarify, all single bonds around it, it's going to be sp3. So there's a lot here to take in, but let's just do a quick recap. We talked about different hybrid orbitals. So there are 3 types of hybridized orbitals. There's the sp3. Let me get my pen. There's the sp3, the sp2, and then the sp. And then there's an unhybridized p orbital, which we'll talk about later. But how do we tell if an atom has one of these orbitals that are hybridized? Well, we look at domains. There can be 2, 3, or 4 domains. In this first example, we have 2 domains. 1 triple bond is 1 domain, and then the single bond on the other side is another domain for 2 total. When it's 2, we have a linear arrangement with 180 degrees of separation, and we have an sp hybridized atom. So that carbon in the red circled in the red, is going to be sp hybridized. Now, when we look on the next example, we see carbon and oxygen, both in green, have essentially 3 domains around it. Oxygen has 2 lone pair domains and then a double bond domain for a total of 3. 3 domains means we're going to have 120 degree separation. It's going to be called trigonal planar. And then lastly, we'll have sp2 as the hybridization. For carbons or atoms with 4 domains around it, we're going to have a tetrahedral geometry with 109.5 degrees of separation. It's going to look like this down here, 109.5, like essentially a tetrahedral shape, like a pyramid with a square base, essentially. With a triangular base. And so we would have those be sp3 atoms, right? So these are the examples of what we can do with that knowledge. We can ask you, this is very high yield. So I'm going to make sure you know this. This is very high yield in the sense that you're going to get problems like this all the time. You're going to get a molecule, and then you're going to be asked which carbons are what hybridization, which atoms are what hybridization. So they could be oxygens, they could be nitrogens, they could be any atom, but the same principles apply. We'll go over more examples later.